Submarines are just incredible. They're silent hunters, deep-sea explorers, really some of the most complex machines we've ever built. And they operate in an environment that's honestly more hostile than outer space, a world of total darkness and just crushing pressure. So the real question is, how do they actually do it? All right, let's dive in and uncover their secrets.
So this is really the central puzzle, isn't it? I mean, how does a 10,000-ton tube of steel just sink on command and then navigate with no windows and somehow survive that insane crushing pressure? It just seems to defy all logic. Think about it, this massive thing has to be a boat that floats and a stone that sinks whenever it wants, all while keeping its crew alive and on course, hundreds of meters below the waves. So to really get it, we're going to have to break this down piece by piece.
Okay, first things first. We've got this underwater paradox, mastering buoyancy. This is the most fundamental problem, right? How do you control whether you float or sink? I mean, on the surface, you need to be a ship, but to disappear beneath the waves, you have to somehow become heavier than the water around you and do it on command. It's a real paradox, and it's one that engineers absolutely had to solve.
And where do you think they found the solution? Well, it wasn't just pulled out of thin air. Turns out, the answer was inspired by nature. Creatures like the blowfish and the Argonaut octopus have been mastering this for millennia. A blowfish, for instance, inflates itself with water. An Argonaut octopus can trap air in its shell to control its position. The principle is exactly the same. You just change your density to control where you are in the water.
It really all comes down to one core principle of physics: buoyancy. Basically, it's the upward force that a fluid, like water, exerts on anything immersed in it, so it's constantly pushing up. For a huge ship to float, its weight has to be less than the weight of the water it pushes aside. So the key takeaway here is, to make a submarine sink, you have to make it heavier. The big question is, how?
And the solution is just so ingenious: ballast tanks. Okay, so picture these huge compartments inside the submarine's hull. To dive, the crew does something that sounds kind of crazy. First, they open vents at the top of these tanks. Then, they open valves at the bottom. Water just floods right in, pushing all the air out. As the sub takes on all that water, we're talking tons of it, its total weight goes way up, and down it goes. It's simple, elegant, and incredibly effective.
So how do you get back up? Well, surfacing is pretty much the reverse process, but with a really powerful twist. Step 1, shut those top vents. Then they pump high-pressure compressed air into the tanks. We're talking a massive blast of air. This air acts like a giant piston, literally forcing all that water out through the bottom valves. Just like that, the submarine sheds all that extra weight, becomes lighter than the water again, and rises right back to the surface.
But not all underwater vehicles do it this way. Military submarines, yeah, they need to surface and dive over and over, so using compressed air totally makes sense. But for the really specialized deep-sea submersibles, think of the one that took James Cameron to the bottom of the Mariana Trench, they have a much more direct method. They just drop heavy, solid ballast weights. Hundreds of pounds of steel just fall away. Instantly, they become lighter and shoot back up to the surface. It's kind of a one-way ticket, but when you're at those extreme depths, it's pretty much fail-safe.
Okay, so we figured out how to get the submarine underwater. Awesome. But sinking is really only half the battle. Now we've got a whole new challenge. How in the world do you drive a vehicle with no windows in total, absolute darkness? This is where propulsion and navigation systems become absolutely critical.
When it comes to powering the vessel, there are really two main ways to do it. First, you've got your diesel-electric subs. They have to run diesel engines near the surface, using a snorkel for air, to charge these massive batteries. Then, when they go deep, they run silently on those batteries. But here's the catch: their time underwater is limited. Nuclear-powered subs, though, they are the true kings of the deep. Their nuclear reactor generates power without needing any air at all. It just creates steam to turn the turbines. And what that means is they can stay submerged for weeks, even months at a time. The only thing that really limits them is how much food they can carry for the crew.
So how do you steer with outside? Well, the sub basically has its own set of super senses. Sonar acts as its ears. Passive sonar is just listening, for the sound of another ship's propellers. Active sonar is more like a bat. It sends out a ping and listens for the echo to map things out. Then you have the inertial navigation system, which is kind of the brain. It uses gyroscopes and accelerometers to calculate its position based on its own motion, no GPS required. And of course, there's the classic periscope, the eyes, but that's only good for when you're up near the surface.
All right, so we figured out how to sink, how to surface, and how to drive around blind. But now,
Now we face maybe the most terrifying challenge of all, withstanding that relentless, crushing pressure. The deep ocean literally wants to squash a submarine like a tin can. Just look at this number, 16,500 psi, pounds per square inch. That is the insane pressure the pilot sphere of the Deep-Sea Challenger was designed to handle. To try and put that into perspective, imagine 3 large SUVs stacked on top of each other, balancing on a space the size of your thumb. That's the force that's crushing every single inch of that hull. It's almost unimaginable.
And this is exactly why building a submarine is one of the most precise engineering jobs on the entire planet. The hull has to be as close to a perfect sphere as humanly possible. I mean, listen to this quote. Even a 1-inch deviation from roundness results in over 30% decrease of maximal hydrostatic load. Basically, if you're off by even a tiny bit, you lose a massive amount of strength. Any flaw creates a weak spot for that immense pressure to attack, and that leads to catastrophic failure. There's literally zero room for error.
So how on earth is the hull built to survive this? Well, the secret is that a submarine actually has 2 hulls. The one you see on the outside, that classic teardrop shape, that's the outer hull, or what they call the light hull. Now, its job isn't to take the pressure, it's all about being hydrodynamic, letting the sub slice through the water efficiently and quietly. And those ballast tanks we talked about, they're usually tucked right in the space between this hull and the one inside.
And this is the real key to survival. Tucked inside that outer shell is the strong inner pressure hull. This is the crew's sanctuary. It's built from incredibly thick, high-strength steel, sometimes even titanium, and this is what bears that unbelievable load from the water pressure. So while the ocean outside is trying to crush it into nothing, the pressure inside stays at a perfectly normal, livable level, the same as if you were standing on the surface.
Okay, so this whole system of ballast tanks is a true marvel of engineering, right? It's the absolute key to a sub's ability to dive and surface. But this very same system, the one that pumps millions of gallons of water in and out, it turns out it has a pretty serious unintended consequence, one that actually affects the entire planet.
Here's the problem. When a ship or a sub takes in all that ballast water in one part of the world, it basically sucks up all the local marine life along with it. Then, when it gets to a new port, maybe thousands of miles away, and releases that water, it can introduce invasive species where they don't belong. A really famous example is the zebra mussel. It basically hitched a ride in ballast water all the way from the Black Sea to the Great Lakes in North America, where it ended up causing billions of dollars in damage to the ecosystem. Because of this, there are now international rules that require ships to treat their ballast water to stop this from happening. So, while we're now figuring out how to manage that environmental side of things, those core engineering principles, controlling buoyancy and resisting pressure, are still being pushed to their absolute limits. And when you take those ideas to the absolute extreme, well, you get something like this, the Deep-Sea Challenger.
I mean, just look at the specs on this thing. This machine is a true marvel. It's built to dive to 11,000 meters. That's deeper than Mount Everest is tall. The pilot sits inside this tiny sphere made of steel that's over 2.5 inches thick. That's the only thing holding back all that pressure. It runs on advanced lithium-ion batteries and has 12 different thrusters just to move around down there. Honestly, this isn't just a submarine. It's basically a vehicle for visiting another world.
So think about it. We've engineered these incredible solutions to conquer the deep. We figured out how to sink on command, how to navigate in total darkness, and how to survive in one of the most hostile environments on Earth. We've built vessels that can literally reach the deepest points on our planet. And all of that leaves us with one final, really exciting question. Now that we've solved the engineering challenges, what's still waiting down there to be discovered?